get knowledge for the innovative development of the products, or it should have some implications of the society. So if you follow these type of two approaches, like either you develop for some products, or you do some applied research, or you do something for the society, definitely the evaluators will evaluate those projects in such a fashion, and they will give you a lot of funding also. So these type of short term programs give you a platform where you could discuss the things with the expert, not only the domain knowledge which you will be acquiring, but also you could have interactions with the experts, that how they could apply, you could apply for different organizations for different fundings in that particular area. So I congratulate once again the department and the coordinators. So my best wishes to all the participants, and I hope during the deliberations you will learn a lot during these 5 days. Thank you.
Thank you very much, sir, for your wonderful words and to grace the occasion. Dear participants, I hope that it will be a great learning experience to all of you. So we hope that you will be interacting with the experts time to time, and we also will try to give you the access to the all the lectures through YouTube and as a recorded videos. So thank you very much, the chief guest and the chairman, head of the department, and the scholars and faculty members and participants to join this inaugural ceremony. Thank you very much. So soon our expert will join, Professor Srinath from Binghamton University, to deliver the first lecture on design and optimization of thermal system. So now the session will resume from 3 p.m. Thank you, everyone.
The meeting link will remain the same
Yes,
throughout all.
the meeting link will remain same for
Okay.
throughout the 5 years.
Link is same, sir. Link is same, sir.
Okay.
There is a 5 to 10 minute interval, and
Yeah.
3 p.m. he will join, sir.
Yes, right.
We have contacted him.
If you, Dr. Devesh, Dr. Sandhya, if you want to give some information also to the participants, I mean, about the attendance and anything which you can tell us right now.
Surely, sir, I would like to add something here, because it means we have chosen the faculty members because it's actually simply a computational course. Means whatever the lecture the participant is going to see here will contain that is the CFD, the computational fluid dynamics, and with the flavor of machine learning, which you have already actually mentioned, sir. Along with that, sir, means there will be lecture like in the first half, and in the second half we have also arranged actually the workshop on that CFD. For the workshop, sir, we have chosen the industry expert actually. So we have chosen the persons. We have selected the person from Godrej who's actually doing the practical job there. And what they are doing, we are using that thermal systems. So that means thermal system means we have chosen from the Godrej, and in that we have what we have selected, because it's a design actually, right? It's a design and optimization. So in the design we have chosen one members, because I mean see, that takes a very long time to to find that person who is specialized in structure, means the thermal structure actually. So after some inquiry, I came to one person, and he agreed with all the permission from Godrej actually. That's Sunil Kumar. So he will take the workshop on structure of the thermal systems like refrigerations and air conditioning. I mean I'm not exactly aware, because I will ask the topic, but he said that I will take a workshop on structure, and there is another Mr. Vinay Srivastava. He will take means he will continue the CFD analysis. So one is like the structure. First we need a structure, and then there is an analysis of the fluid flow and the fluid dynamics there. So
Correct.
we have chosen that, and along with that, because we have one lecture of the artificial and machine learning. So based on that, then we have selected one workshop on the AI actually. Machine learning also. So because AI is a vast area, sir, that will need a separate actually. But what we are trying here, we have means we have tried to means include at least one software. Okay, means the knowledge of that software, so that participants can understand that software at least.
Okay.
and they can go in that software elaborately if they want. So that will actually going to boost that knowledge of
Okay.
the or the idea of the machine learning.
Okay, fine. Dr. Siddha, I think our first speaker has joined.
Yeah, I think he is
Dr.
joined now.
Shrikant, yeah, he joined and then left.
Hi everyone.
Ah,
Hello,
yes.
Professor.
Yeah,
Um,
this is Shrikant.
yes,
Sir, welcome, sir.
welcome, sir.
Thank you so much.
Yeah, we just ended with the inaugural ceremony, and
Okay.
we are great to
I,
have you,
I
sir.
request Dr. Satyendra kindly introduce Dr. Srikant to our participants. Okay, sir, with you. And one more thing, I think that course is live on the YouTube. I think Dr. Satyendra, link is active.
Yes, the link is active.
Okay, so now it will be available on YouTube also. So if anyhow the participant is not able to join, they can see that lectures of this short-term course on the YouTube on the later stages in the future.
Yeah,
Okay,
thank you,
now can
Dr. Vish. I will be grateful to introduce our first speaker, uh, who is the most relevant speaker we have as per the theme of the short-term course. So I welcome Professor Srikant Rangarajan, who is a faculty in the School of System Science and Industrial Engineering in Brington University, USA. Professor did his PhD from Indian Institute of Technology, Madras, in 2017. He obtained his bachelor's. He did his master's as well from the same institutions. Uh, and of course, we all know that IIT Madras is one of the top-ranked institution of the country. He obtained his bachelor's in engineering in 2011 from Anna University, Chennai. His research interests includes energy storage management systems, electronic packaging, digital twinning for electronics and batteries, thermal energy storage, thermal management of electronics and data center cooling. Professor is also the author of the book on phase change material heat sinks, a multi-objective perspective. So prior to joining the School of System Science and in the Industrial Engineering, Professor worked as an associate research professor in the Department of Mechanical Engineering at Sony Bringmonton with Professor Bhagat Samakia. So I now request the professor to start with the first opening lecture on the design and optimization of thermal systems, particularly on microchannel cooling. So over to you, professor.
Thank you so much, Dr. Satyendra, and hope I'm audible.
Yes, sir, you are loud and clear.
All right. Thank you so much, Dr. Satyendra, for a warm introduction, and thank you all for your kind attendance. So I'm just going to go ahead and share my screen. Okay. Are you able to see my PowerPoint presentation on full screen mode?
Yes, sir.
Okay, thank you so much. So, good afternoon, everyone. This is Srikant Rangarajan. So, today my talk is going to be on design and optimization of electronic cooling systems. So, the agenda for today's talk is I would have a brief introduction about the problem in electronic cooling, then evolution of electronic packaging and thermals, and what is the new age problem and targets for electronics thermal management. And then I'll also discuss about the limits of the current cooling technologies and a little bit about the fluid selection and some case studies on improving the system's energy efficiency by using different cooling technologies. Then I will also talk about the phase change based cooling and also about the limits of embedded cooling technologies, future directions, and summary. So the introduction is, as we all know, today the climate change is really alarming, and whatever research topic we try to do, we are trying to make it more and more sustainable, and with very less impact on the environment. So you can see that the mitigations can be increasing the sinks, reduce sources, improve the energy efficiency, try to make use of renewables and carbon sequestration. And when we talk about electronics today, it is electronic equipment is almost inevitable in today's life, and has become a part of modern society. From smartphones and laptops to appliances and wearable devices, they are integral to a lot of applications for today. And the Internet of Things further amplifies this perception, connecting various devices and enabling remote control and data exchange. And the sustainability and environmental impact is something that I would also want to touch upon. So electronics consume an increasing fraction of world's annual footprint, and thermal management enables higher performance and reduced junction temperature, and can substantially reduce the leakage and the total power consumption of the electronics. So the electronics industry's forecast, as you can see here, that from 2014 to 2017, the smartphone boom stagnation, and then from 2017, the industry growth cycle resumed. And now we are seeing a huge surge in data centers and other digital technologies. And because of a lot of this digital revolution that is going on, the data centers are becoming more and more prominent in the market. So let's take a brief look upon. So I'm going to talk about a lot of this experimental, numerical, and machine learning based techniques for modeling and optimizing the thermal management systems. But before that, I just want to touch upon a little bit of the history on the evolution of electronic packaging and thermals. So the first one is like the Moore's law, and as we can see from the Moore's law, the number of components that can be packaged within a single chip almost doubled for every 18 months. And we did see that around 2010, the trend kind of plateaued because we were not able to package more and more, and the performance did not improve much. And that's when the concept of heterogeneous integration came along. So in 2010, we encountered this very big issue about the dark silicon. So the dark silicon, it means that there is a certain portion on the electronic chip that cannot be used, or it becomes more of unusable because of the thermal problems. So for example, if you want to get like a high performance, you have this transistor scaling, and then we do the integration. And because we do this integration, we also have this increasing leakage power. And because of this, we get a high power density. And because of the high power density, we get this high temperature. The reason why from power we get this high temperature is because of the limited cooling solutions. And because of this high temperature, the chips run into thermal issues. And because of the chip running into thermal issues, people are not able to utilize the complete footprint of this electronic chip. And there are certain portion of the chip that becomes unusable or inactive, and we term that as the dark silicon. And because of this dark silicon, there is a forced inactivity. We are only able to use a certain area of the chip, and it leads to low performance. So the moment we want to switch from a low performance to high performance, it is only limited by the cooling solutions. It is only limited by the thermal challenges. So one effective technique is to make sure that we develop like very aggressive thermal management solution, which are superior in terms of heat transfer and also more energy efficient and sustainable. So the projections on dark silicon, as you can see here, so from the 45 nanometer chip all the way to the 8 nanometer chip, you can see that the region which is indicated in red, this region is the total area of the chip that is really inactive. You can see that it just grows over time. And there is now the time where we try to make use of this entire chip or maximize the chip activity by making sure that all part of the chip is able to operate under safe operating condition. So that is going to be the main aspect of doing this thermal management solutions, and making sure that we come up with a solution that just doesn't reduce the maximum temperature, but also enables all the part of the chip to operate under a safe operating level. So the heterogeneous integration is a technique that was thought about as a solution to the dark silicon issue, and also it sustains the Moore's law. So the chiplets, which is nothing but a smaller form factor of the chip, adds another level of flexibility because the chip size can be adjusted according to any condition required for a particular function. So When we spoke about dark silicon, we did understand that there is going to be some portion of the chip which is going to be inactive. So it is better to just design chips of that area where we can completely make use of it and have multiple of such chips which can later be integrated to form one single package. So this means that the unused parts of the chip can be completely eliminated instead of being put to sleep, and additional functions can be placed on different small chips. So the ability to package more functions on the chip is weakening, but the power consumption is also shrinking. So now the advent of heterogeneous integration is actually helping us progress in terms of performance, but it is also bringing in other new challenges with respect to thermal. So this is a question that researchers should work on because it generates a lot of heat and you can't deal with it anyway. So you want to maximize the performance and operate it in a more reliable fashion, which means thermal is the only option. So let's look into the brief history on the evolution of transistor packaging and thermal solution. So the first, in 1904, there was an advent of this vacuum tube diode. And then in 1926, we saw the evolution of the field effect transistor. And in 1935, we saw the evolution of air and liquid cooling of vacuum tubes. And it was in 1955 where NASA publishes its first document on electronic cooling. So we can see that in 1955, the electronic cooling as a field gained its prominence, and there was different cooling technologies that was discussed. However, if you see that the first chip that came as a part of this IBM's thing was just 0.3 watts per chip, you can see the heat flux or the heat was very low. It's just 0.3 watts per chip. And it was cooled by air and liquid cooled heat sinks, and it was first commercialized by IBM. And in 1965 is when we saw this advent of this classical Moore's law, which states that the number of transistors that you can package within a single chip can double for every 18 months. And that time we were talking about 10,000 nanometer chips. And in 1980, there was a seminal publication from Tuckerman and Pease, who spoke about 790 watts per centimeter square of heat, which was being removed by silicon embedded liquid cooled microchannel. But this one never made it to the market because people were embedding the cooling solution directly onto the chip, and this was going to be a not so pragmatic solution from a commercial point of view. So after this, in 1987, we did see that IBM had a immersion cooled chip, and they also call it as a Cray 2 using FC72 as the fluid. And the other thing was the IBM's jet impingement cooled modules by using FC72 as the cooling fluid. And in 1993, it was the first time that the thermal interface material was identified as the thermal bottleneck, which means that people understood that rather than the external heat sink, and then is consumed by the electronic chip while it's not actually doing the computation, rather it is just wasted as heat. So the leakage power started to rise as we shrunk from 10,000 nanometer chip to 45 nanometer chip. And because of this leakage powers rise, the Dennard scaling law failure, which means that you can no more scale the voltage and the transistor size. And then in 2000 to 2010, this was the era of dark silicon. So people accepted that there will be certain portion of the chip because of the overheating problem, which will be unused, and we may not be able to completely make use of it. And 2010 marked the era of heterogeneous integration. So it was 22 nanometer technology and 300 watts per centimeter square. So now, before 2010, the Moore's law could be said as packing more transistors on a silicon chip through transistor scaling. Beyond 2010, what heterogeneous integration really meant was packaging more silicon chips in a given space. So both are very different. Like rather than packing transistor, you want to package more and more chiplets, the silicon chip, which is completely utilized in a given space. And in 2019 to 2021, we did see the 5 nanometer chip, and now the chip power is close to 1 kilowatts per centimeter square. And again, the TIM, the thermal interface material, was identified as a thermal bottleneck. And this is the era of heterogeneous integrated packages, right from 2010 to 2021. And now, because of today's AI workloads and many data centers are running this AI workloads, we are seeing that the heat flux has rose to 5 kilowatts per centimeter square. And today, none of the cooling solutions might be really viable to remove such a high heat flux. And today we are talking about the era of embedded cooling, where we want to embed the cooling solutions directly onto the electronic chip without the use of thermal interface material. So the problem is heat becomes increasingly higher. That's the problem we saw in 1900. So from 1926 to 2010, the only problem is heat is becoming increasingly higher because you don't have any heterogeneous integration. Now, heat becomes a packaging constraint, right, in 2010. And after 2010, now the heat becomes increasingly higher. In addition to that, it also becomes increasingly inaccessible because of the heterogeneous integration. You're packaging more and more chips. So for the cooling solution to access the hottest part of the chip, it becomes more and more difficult. And huge deviation between the maximum temperature and the average temperature of chip is causing a lot of reliability issues. So let's look at the real problem of today's electronic thermal management. So is the real question that we want to answer is the heat really accessible? And how does the today's package looks like? So this is a figure from the National Institute of Science and Technology, and you can see that the processors are not in a very close proximity to cooling solution, and you have a number of series resistance that is between the processor and the heat sink. And this is really making it difficult to access the heat even before we think of removing them. And this introduces this whole new field of spreading and moving the heat, which is becoming increasingly essential. So the optimization opportunities for heterogeneous integrated packages. So what you see here is the conventional way on which a cooling solution is packaged onto an electronic chip. So what you see on the bottom is an active device, core or a multi-chip module. And then you have this first thermal interface material. And then there is an integrated heat spreader or a lid. So this lid, the TIM1 and the active silicon device together is called as a chip package. And the chip package is now getting attached to a heat sink through another thermal interface material. And then we have this either the copper heat spreader or the vapor chamber sitting on top. And then we have this micro channels or air-cooled heat sinks on top, which is actually removing the heat. And what you see on the right-hand side are the optimization criteria. And what you see on the left-hand side are the constraints driving this optimization at each of this level. So if you design that, if you want to embed the cooling solution directly onto the device, that's called as the technology 1. And if you decide that you want to embed the cooling solution directly onto the top of the lid, that's called the technology 2. And then the heat spreaders as such can be the technology 3. And the conventional cold plates and heat sinks are coined as the technology 4. So all of these technologies are interesting, but what decides the implementation is the heat flux levels from this active device. So if the heat flux is, let's say the silicon device is more like localized and it is having a very high heat flux, and if you do your calculation from first principles and you see that by using technology 4 you may exceed like 100 degrees Celsius of the chip, then you might want to see if I can do a technology 2 or a technology 1 which will maintain the chip temperature at a safe operating limit. But however, the technology 1 might sound very interesting from a heat transfer perspective, because here you are embedding the cooling solution directly onto the chip, which is the direction of increasing energy efficiency. So which means as you try to implement your cooling solution in close proximity to the chip, then you are more and more energy efficient. However, the more away you stay from the electronic chip, that's a direction of increasing reliability. So there is always a conflict. So the moment you choose to implement technology 1, you also see that the fluid choice has to be strictly dielectric. Now you can't use liquid water for your cooling solution. You can only use dielectric fluids because you don't want the fluid to interact with your active components in your electronics. So from a heat transfer perspective, water is known to be the best heat transfer fluid with a very high heat capacity. However, now that you're restricted for not using water, then the heat transfer performance might slightly come down, and also you don't have much area to remove the heat. So that's a disadvantage with technology 1. However, from a technology 4's viewpoint, you can see that you have a much bigger area, and you can also use liquid water. So from a heat transfer perspective, it might seem very, very attractive. But the problem is that you have a series of resistance that is sitting between the active device and the cooling solution, which means the temperature can automatically rise even before the heat is reaching this particular cold plate. So it is just from a first principles calculation we can decide which technology to use, but all of these technologies are being currently used for different applications. Now, the thermal management of electronic systems can be categorized into all of these categories that is listed on this particular slide. So the first basic cooling technology is called the air cooling, where the fluid that is used is air, and then you can also use vapor chambers and heat pipes, and this is constantly being used by the industries. So the second technology that you can use is single phase liquid cooling, and the main task here is to design an optimization of heterogeneous integrated packages and heterogeneous packaging conditions which have to be mimicked. In single phase liquid cooling, mostly again liquid water is being used as a heat transfer fluid. The third and fourth technologies are the phase change based cooling, which is called as the two-phase liquid cooling, where the liquid is changing its phase from liquid to vapor. And in case of immersion cooling, there is no pumping. So which means that there is a nucleate pool boiling, which is more of a passive technique. And in case of a pumped two-phase cooling, the two-phase coolant is constantly being pumped and circulated through the microchannels, and then the boiling is happening. And the fifth one is the rack level cooling. So this is in data center level. So if you have an electronic chip, if it's part of a server, and if it's going to be housed in a data center, the common way to arrange these servers are in the form of racks. And we'll also see some case studies regarding the rack level cooling's experimentation, modeling, and optimization. And the final one is the chip level, where you want to have the entire cooling solution embedded directly onto your electronic chip. Now let's look into the cooling limits. So the cooling limits again kind of help us choose the cooling solution. For example, if I want to remove a particular heat flux, so on the x-axis you can see the heat flux, and on the y-axis you can see the complexity, cost, and risk. So on the lower left you can see the forced air cooling, which can remove a very low heat flux, but it's going to be the most reliable, less complex, and a cheap cooling solution. However, as we want to advance in the heat flux, you can see that the next good option is a single phase liquid cooling. And as we move to two-phase cooling and immersion cooling and embedded cooling, though the heat flux is rising, you can also see the complexity, cost, and risk is also rising. So most of the industries, the reason why they are resistant towards these kind of advanced cooling technologies is because it can interfere in the chip design and then cause a lot of complexity with respect to the design of chip and the packages. So the complexity can be high and the cost can also be high, which means the risk is very, very high. And in the last, you see the forced single and two-phase liquid cooling with printed fins directly on the chip. So this is using the additive manufacturing technique. People are trying to deposit and manufacture the cooling surfaces directly on the chip, and they use the single and two-phase liquid cooling as their solution. So the Takaraman and Pease paper, which was published in 1981, they showed that embedding the cooling solution directly on the backside of the chip using single-phase microchannel cooling can remove heat up to 790 watts per centimeter square. But today we are talking about more than 1 kilowatt per centimeter square. So we have to go for more and more aggressive cooling solution. So one of the highlights of the research that we have done for heat transfer limits of air and single phase liquid cooling is that we really worked with industries, and then for the industry norms and the constraints that were posed by the industry, we were able to publish some of the cooling limits for air and single phase liquid cooling, which are already available in the literature. You can go through this particular link if anyone is interested. So as you can see from the table, the advanced air cooling with integrated heat spreading elements like vapor chamber and heat pipe can remove heat up to 55 watts per centimeter square for a thermal budget of 50 degrees Celsius. So the thermal budget here means the temperature difference between the chip and the cooling fluid. So in a 50 degree C thermal budget, we are able to remove 55 watts per centimeter square. And whereas for water cooling, which is a liquid cooled cold plate single phase, we are able to remove 170 watts per centimeter square for the same thermal budget of 50 degrees Celsius for a 4 centimeter square chip area. So these are the results that we have published so far. So we are continuing to work in establishing the cooling limits for other cooling technologies. So as you can see here from our analytical framework, we are also able to see that for air cooling and single phase liquid cooling, the cooling limits are highly different by an order of magnitude. And as we want to achieve more and less thermal resistance, we have to go for single phase liquid cooling. Now, what is the future roadmap for air cooling versus single phase liquid cooling? Where does the opportunity lie? So if you look at the air cooling, the most of the resistance is actually coming from the heat sinks resistance, and there is a minor resistance coming from the thermal interface material, and a very negligible resistance that is coming from the heat spreaders. So anything, any research that we can do to reduce the thermal resistance of the heat sink itself can contribute to the energy efficiency of air-cooled heat sinks. On the contrary, if you look into the liquid cooling, the 50% share of the resistance is actually coming only from the thermal interface material, and the remaining is actually coming from the heat spreader and the heat sink. So you can see that because of the high heat capacity and the heat transfer coefficient of the liquid water, the heat sink's thermal resistance is actually very low. So there is less opportunities there to optimize the heat sink's thermal resistance. However, there's a huge opportunity with respect to the thermal interface material, because that's going to be the real bottleneck in removing the heat when it comes to liquid cooling. Now for the cooling solution, we want to select the fluids. So the fluid selections can happen by using some figure of merits that are already published in the literature. So these figure of merits are actually derived from the governing equations, and if we are able to arrange the non-dimensional numbers in the governing equation in a certain pattern, we'll be able to see that we can do this figure of merit analysis for different cooling solutions like natural convection, forced convection, immersion cooling, and flow boiling. So for natural convection based cooling, or beat any cooling technology, you can see that liquid water is always the best. So higher the value of figure of merit, it means that there is a higher cooling capacity. So the water at any cooling scenario gives the best heat transfer result, and then it's followed by other fluids like fluorocarbons and hydrofluoroethers and NOVAC and all that. So if there is any new fluid in the market, or if you intend to use any new fluid, we can always do this analysis how much this is going to perform. So this entire figure, what would be the figure of merit of using different fluids. And today for the fluid selection, it is not just the figure of merit based upon the heat transfer, but people are talking about the global warming potential and the ozone depletion potential. So we want to choose fluids that are more sustainable and then cause very less impact to the environment. Now, why do we want to do this electronics thermal management? As you can see here, this is a slide about a data center which is housing a lot of electronic equipment. So the electronics thermal management systems in high ambient temperature environment and water scarce region needs high innovation and package integrated thermal technologies, which means that if I'm the high performance computing chip generally operate at a limit of, let's say, 80 degrees Celsius. And if you want to house a data center at a region where the ambient temperature is 50 degrees Celsius, which means that you only have 30 degrees Celsius delta T. And if you want to remove a kilowatt of heat from one chip, then you can now calculate the available resistance. So for let's say for a 30 degrees Celsius delta T, if you want to remove 1 kilowatt of heat, then the thermal resistance is 0.03. So if you want to achieve a thermal resistance of 0.03 for this entire data center put together, you see that first, what is in close proximity to this high performance computing chip is the heat collection systems. So these heat collection systems are oftentimes the cold plates or the heat sinks. And then you have this heat transport systems. These heat transport systems are nothing but the coolant distribution unit that is circulating the coolant. And then you have this heat rejection systems, which are the cooling tower or the dry coolers. And then you have this ambient. So from the high performance computing chip, you can very well see that the heat has to travel through all of the system before it reaches the ambient. And now if you want to have an aggressive thermal resistance target of, let's say, 0.03 Kelvin per watt, then you have to make sure that the heat collection systems are well optimized so that they can operate at very, very low thermal resistance. And this figure also emphasizes one more thing. Like if for example, if you have a power supply that's entering a data center, And the power supply is consumed by two main components. One is the IT systems and other is the cooling systems. So if you want your IT system, like your electronic chip, to operate in a reliable fashion, then it is well understood that only if your cooling systems are reliable, then your IT systems can be reliable. So the reliable operation of cooling systems are more important, and this reliable operation of cooling system can keep the electronics well under the safe operating limit, and that's when you can really go for very high performance computing. So the main objective or the goal would be to minimize the ratio of the cooling power to the IT power. And as the T ambient increases and for very large chip power, then it becomes necessary that we go for very aggressive thermal management solution. So to run the system, let's say at higher inlet temperature with less energy usage, there is a need to minimize the chip to coolant thermal resistance, which means the chip that can run cooler can be more energy efficient because it draws a very little chip power, because the leakage power that is consumed by the chip is a direct function of the temperature of the chip, and the cooling integrated with chip can be more and more energy efficient. So the system level targets for electronics thermal management, this is defined by the ARPA-E cooler chip program. And as you can see here, the main objective is to minimize the ratio of the cooling power to the IT power to be less than 5%, which is a very, very aggressive target. So today the data centers are operating anywhere between 30% to 40%, but now the new age target has to be 5%, which means the cooling power has to be less than 5% of the power consumed by the electronics. And you have to minimize the die level thermal resistance, the chip level thermal resistance, and the system level thermal resistance. And the target resistance at die level is less than 0.01 Kelvin per watt for fluxes above 500 watts per centimeter square. And for next generation of electronic systems, the IT power, which is the electronics power, will be a function of the cooling power, because if you spend more power on cooling, then you will be able to reduce the temperature of the electronics, which means the electronics can draw very little power because of the temperature, and that will be the interplay that we might want to optimize. So as we shrink the transistors, as we get to more and more advanced technology, this might be the case, and we have to co-optimize both the IT power and the cooling power. So keeping in mind all of this, my research focus is addressing climate change, requires accelerating the development of sustainable alternatives to energy and water intensive technologies, particularly for heterogeneously integrated packages and rapidly growing infrastructure such as data centers and cloud. So the solution is direct on chip phase change based cooling solution. The reason for direct on chip is to make sure that the accessibility to the heat issue is addressed. You can be in close proximity to the chip. And phase change based cooling solution is because you can achieve a very, very low thermal resistance because of the latent heat utilization. And the challenge is it is not so easy to implement this on the real time because of the reliability issues with the real-time deployment. So unlocking some insights with AI, because now that you want to use direct on chip phase change based cooling, AI is a valuable tool for thermal management scientists. So because AI is really transforming the way the phase change heat transfer is modeled and deployed by increasing efficiency, reducing cost, and enabling smarter decision making. So my research focus, keeping in mind all of these things, is going to be on digital twinning of electronic systems, on-chip pool boiling, and on-chip flow boiling. So let's look at what exactly is digital twinning of electronic systems. So digital twin technology is a digital replica of a physical object, person, system, or process contextualized in a digital version of its environment. And digital twins can help make many kinds of organizations simulate real situations. Even before you want to go and fabricate and test a technology, if you're able to digitally twin them, if you're able to look at the virtual replica of that, then you save a lot of time, energy, and money before you do that. So the 6 main applications of digital twinning are system prediction, system simulation, asset interoperability, and system visualization, maintenance, and product simulation. So the main focus of my effort on digital twinning would be the system prediction, or it's also called as the predictive model. So the digital twins for electronic systems have become a groundbreaking concept in the field of electronics packaging and electronic systems, because you want to digitally simulate the working of electronic systems. And in an era characterized by rapid technological advances and increasing complexity in electronics products, digital twins offer a revolutionary approach. And these virtual replicas of physical semiconductor circuit thermal management systems can help provide invaluable information. And this enables real-time monitoring, analysis, and optimization. And this innovative technology not only improves product development, but also performance and helps in our sustainability goals. So the modern and future data centers really need digital twins. So the digital twins, which is the virtual models of data centers, can help designers operate plan to cool their facilities optimally, and operators can evaluate the advantages and disadvantages of different cooling strategies and test multiple deployment scenarios. And given the dynamic nature of data centers and electronic systems, understanding how equipment responds to new setups is crucial. Now, the electronic cooling systems in data centers, they have like different levels, starting from the bottom right, which is on the chip level. So you can bring in your thermal management systems directly to the chip. And you can also try to do this in the module level, where you package the chip and then bring in the cooling solution. And then on a server level, because this electronic packaged chip can be a part of a high performance computing server, and you can also try to implement your cooling technology in the server level. And then if you're taking it to a data center, the level 4 would be a rack level, and the level 5 would be a room level. In all of these system levels, it is very important for us to properly acquire experimental data, which involves a lot of measurements and instrumentation. And also there is a need to develop like modeling capabilities for thermal management solutions in all of these levels, and also like finding opportunities to optimize so that we are operating energy efficiently for all of these levels. So this is going to be the main objectives of my research, and I'll show case studies from each of this in the coming slides. So here you can see that the strategic areas and future application of digital twins will extend from air cooling to single phase liquid cooling to system level modeling, and also machine learning based control and prediction in data centers. Now, the liquid cooling, which is what I will be talking, the liquid cooled microchannels. So the massive growth in data centers have raised interest and regulations for cooling system designs and optimization. And liquid cooling has a potential to revolutionize modern data centers. And by effectively handling heat through direct to chip and immersion cooling, data centers can achieve high efficiency and reliability. And understanding the phase change heat transfer is very important to numerous applications. And though the phase change heat transfer looks very attractive from a heat transfer perspective, because it can help us achieve a very low thermal resistance, it also has a lot of shortcomings in terms of reliability and modeling. Especially on the modeling front, we don't have good correlations or modeling techniques that can be computationally inexpensive. So most of the modeling techniques are computationally expensive. It takes a lot of computational resource to model phase change. So now there is a need for us to develop like good modeling approaches, and AI-based digital twinning can offer numerous advantage in phase change-based thermal management solution. So let me show you a case study on how AI is really transforming the on-chip pool boiling process. So the objective of this work is to demonstrate the feasibility of a comparative visual framework capable of quantifying changes in heat flux, laying the groundwork for future development of predictive, non-intrusive diagnostics and boiling heat transfer. So what we want to do is, like, if I'm in a real-time scenario, if I don't have access to the chip, the electronic chip heat flux and the electronic chip's temperature, just by looking at the phase change morphology through the bubble dynamics, will I be able to construct the boiling curve? So can we diagnose the regime shift in the boiling curve just by using the visual information is the answer that we are trying to achieve. So the problem statement is that understanding phase change heat transfer is important to numerous applications, especially the thermal management. And the main challenge my research addresses is modeling phase change heat transfer, specifically in the context of boiling. And this phenomenon is inherently complex due to intricate interplay between the fluid dynamics, the heat transfer mechanisms, and phase changes. And traditional modeling approach often falls short in capturing the rapid fluctuations and nonlinear behaviors of characteristic boiling. So you can see here that though this is for a steady state heat flux, you see that the morphology of the bubbles continue to evolve with time. And the moment I change the heat flux of the bubble, this morphology is going to
I'm sorry, Professor, for this disturbance. You may please continue. Professor, please unmute your device. I had to mute all the participants, so you also got muted.
Am I audible now?
Yeah, you are audible.
Okay. Is my screen visible?
Yes, Professor.
Okay, thank you. So for the purpose of modeling this phase change heat transfer, the precursor to that is the data from the experiments, right? So what we did is like we constructed an experimental setup which had like a high-speed flow visualization by using some high-speed cameras, and then we did make use of the shadowgraphy technique to capture the morphology of the bubbles. And by using this, what we did is like we fed the videos and the images that were captured about the bubble morphology into an AI model. So what the AI model does is that it takes into the account the high-speed images, and what it constructs is called the feature matrix. So the convolutional neural network, which we use here, has convolution operators, which has the ability to extract the feature matrix. So the convolutional operators are trained across a different diverse set of images, like for example, the images of animals or images of objects, and they're well trained to capture the features. So the moment I input an image of a bubble or a boiling process for a particular heat flux, the AI model has a capability to acquire the features and then construct a feature matrix. So one feature matrix is assigned to one heat flux, and then we are able to identify that particular heat flux by just inputting the data of the image data of the bubbles. And that feature matrix is used for training the neural network. So here, what you see here is the masking. So first, what we want to do is before we get the bubble data, the first thing what masking technique that can really mask the entire and mask the bubble, then we can extract a lot of features. In addition to the features, we also try to extract the bubble size, the number of bubbles, and the bubbles velocity, and all of that. All of this data gets into an input to this AI model, and what we first do is a supervised learning. So what we do is like we tell that AI model for a particular bubbles morphology, this is the heat flux. So optimization of the data input to the training process can actually play a much crucial role. But the final ultimate goal of this work is not to have it as a supervised learning, rather to have like an unsupervised learning. But the only priority that we want to give is the critical heat flux. So as you can see here, this is the boiling curve, which is the heat flux versus the wall superheat. So as we keep increasing the heat flux, the wall superheat increases until the critical heat flux, after which for even a small change in the heat flux, you can see that the temperature shoots up. So we are trying to acquire the bubble images for all of these heat fluxes, and then we are trying to use that to construct the boiling curve. So rather than having the boiling curve by making temperature measurements, we want to first just look at the images and then try to replicate the boiling curve, and then try to come up with if there is any pattern that we are able to observe. So you can see here that this is our experimental setup. At the bottom, we have room for temperature measurements, and at the top, we have room for image capturing. And from the top, from this window, what we capture is like the morphological similarity of the images between any two heat fluxes. So you can see that the similarity is very high in lower heat fluxes, which means even if I change the heat flux, the bubbles patterns that are evolving look very, very similar. And as I keep increasing the heat flux, I see that the similarity reduces. And as I approach the higher heat flux, the similarity just plateaus, which means they're getting high and high dissimilar. And here you can see the complement of the wall superheat. So using the temperature data from the bottom, what we try to calculate is the value of the wall superheat, and the complement of this wall superheat is something that I'm plotting here with respect to the heat flux. So this demonstrated that this metric is physically meaningful by showing its strong correlation with surface superheat, enabling identification of key boiling regimes. So now, what is the impact of doing all this? So here, the plot that you see has been generalized across various experiments for different surface and fluid combination. And you can see that this morphological similarity that is just purely derived from AI seems to follow the same pattern, which means even if I did not know the heat flux, I can be quite certain that this pattern is going to be followed, and I'll be able to extract the heat flux values for each of this point if I know only one prior point. That could be a critical heat flux or that could be an intermediate heat flux, but I could see that the pattern is more generalized. So the method's ability to detect key inflection points using only a few image pairs, such as that it can be effectively deployed in scenarios with minimal training data. And we also position this framework as a scalable, data efficient, and non-intrusive alternate to conventional sensor-based methods, making it highly attractive for electronic cooling applications. So the purpose is that as you move towards higher and higher heat flux, you want to make sure your system is able to diagnose it and alarm us, because you may reach the critical heat flux very, very soon. So it's important for us to know at any given point, any given operating point, you want to know how close you are to the critical heat flux. So this method, just by looking at the morphological similarity between two neighboring heat fluxes, can inform us of that data. So the next case study I want to show is the feedback-based cooling system. So for this purpose, we are using a Dell R520 2U server, which is essentially air-cooled. And you can see that these are the fans that are operating in the server, and these are the two air-cooled heat sinks, two aluminum air-cooled heat sinks, and they both are sitting on top of a CPU. The CPU, the maximum power it can generate is close to 120 watt. So here, what we try to do is like we are trying to have an IR camera from the top, which gives us a temperature distribution. And then we're also having some thermocouples on the heat sink. We are also having thermocouples on the bottom of the heat sink. And we are also trying to get some IPMI data on the power and temperature of the chip. And we have instrumented it in such a way that we'll be able to get both the temperature data and also data from the IT side. So this is more of a holistic approach. So not just data from the thermal side, we also want to get data from the IT side, such as the CPU utilization, the CPU temperature, and the power consumption and the fan speed. So all of this together, what we did is like we wanted to understand the relationship between the chip workload and the fan speed. So the fan speed is the cooling system here, and the chip workload is the IT's power load here. And we first wanted to understand if the workload increases, how much does the fan speed automatically ramp up? And as you can see here that when the CPU's power is actually going up, you can see that the fan speed is also ramping up accordingly to maintain safe operating temperature. So in order to understand this better, we wanted to develop a machine learning based algorithm that can help the cooling system act proactively whenever there is a spike in the workload. So this is a CPU I was mentioning. So we have two CPUs on top of which these heat sinks are placed. And what we see here is that as we keep stressing more number of cores within the electronic chips, like let's say we stress 2 or 4 versus 8 versus 12, we see that more cores we utilize, more power is being drawn by the server, and because of this, the efficiency of the server is actually going down. And this is a very smart system. So depending upon the workload, the cooling system is able to either pump more air or less air, which is a smart system, but certainly it's not an optimal system. So we have there is a huge opportunity still exists in air cooling to make the systems more energy efficient. So as more and more cores are getting stressed, it is not necessary that you have to ramp up the fan speed always. Rather, you can try to set a threshold limit and then try to make the cooling system more and more proactive. So the next case study that I want to show from a modeling perspective is thermal aware core hotspot alignment in 3-dimensional integrated circuits. So what is a 3-dimensional integrated circuit? So the norm for heterogeneous integration to package more and more chips in a given footprint also provides opportunities to stack one chip over other, and this is in a 3D format. So you can see that the chips are placed on top of each other, which means in a given aerial footprint, you'll be able to get a very high power density. And for this study, we worked in close collaboration with industries, and then we were able to get some good data about the hotspot. So this is a chip footprint, one chip footprint, and you can see that there are multiple hotspots, 3 hotspots. Like that, on all the 3 chips which are stacked on top of each other, there are 3 hotspots on each of the chip. Now the question is, how do you optimally arrange these hotspots in this chip so that you can achieve like a very low temperature and good temperature uniformity? So the details of the hotspots are here. So we have 3 hotspots. each are of different size. The first hotspot is 1 by 1 millimeter square. The second hotspot is 2 by 1 millimeter square. The third hotspot is 2 by 2 millimeter square. And you see that the heat flux is different and the power generated from each of this is different. So you want to find out how do you optimally arrange them. So we are trying to define like arrangement parameters, which takes into account the centroid of the arrangement and the centroid of the entire chip. And we try to find out what is the difference between the centroid of the arrangement and the centroid of the chip, with which we can gauge if these hotspots are getting crowded closer to each other, or if they are well spread out from each other. So spreading out these hotspots are always good from a thermal perspective, but since we have multiple chips on top of each other, these things, even if they are spread out on one chip, can actually become a problem if they have the same location on the top chip, because it can become an overheating issue. So it has to be spread out from a whole volumetric perspective, which means if I spread out the hotspots in this manner in one of the chip, in the next top chip, I don't want to spread it in the same way, rather than occupy different locations. So it's a very complicated problem. And since it's just conduction based, we can get a lot of solution and then train a machine learning model to identify some of the optimal solutions. So we used a sampling algorithm that can accept the sample based upon the heat transfer principles. And we also used genetic algorithm to optimize the location of the hotspots. So here what we do is we use a Latin hypercube sampling, and we generate a lot of samples for the hotspot position. And there are some certain constraints from a common sense perspective, that the hotspot should not overlap on each other within one die, and the hotspot should not overlap with each other between the two dies as well, right? So we kind of give those constraints right in the sampling process, because we don't want to include them as a part of the optimization, because they are trivial solutions. So we exclude the bad trivial solution in the sampling itself. So the sampling is able to accept and reject a sample. And when we accept a sample, we run the case for the conduction-based solution with a varying heat transfer boundary condition, and we are able to then optimize and find out the optimal location. So you can see here that we did not want to have a constant heat transfer coefficient on the backside of the chip. Rather, we want to have a varying heat transfer coefficient with respect to the space. So you can see here that the heat transfer coefficient is varying, which means we have you can assume this to be a parallel microchannel with the liquid entering at one end and leaving on the other end. So the heat transfer coefficient is varying, is very high at the entry, and then it slowly decreases as we move towards farther spatial locations. And you can also see that the local fluid temperature is increasing because of the caloric heating. So this is the heat transfer coefficient we had, and this is a schematic of the optimal arrangement that we have obtained for the given limitations and conditions that we impose for the optimization problem. Now, to confirm that this is an optimal solution for this arrangement, you can see that this is the solution that is pertaining to the arrangement that I showed in the previous slide. And you can see that the temperature here is more uniform, and it's also the least among most of the solutions that we saw from this. So AI-based modeling can not only speed up the computation, but it also can help identify solutions that can minimize the chip temperature, and also it can maximize the temperature uniformity. You can see here that the temperature is much more and more uniform. But if you ask me if this is a global optimal solution, I would say I don't know, because this is only valid in the range that we have trained. So as I keep expanding my training range, I'll be able to get more and more global optimal solutions. So this is just a way to demonstrate that AI-based solutions, especially if you are able to derive some arrangement parameters, can really change the game. It can really help you obtain this optimal solution in a much quicker fashion. The next topic that I want to talk about is the pumped two-phase cooling in both chip level and rack level. So why pumped two-phase refrigerant cooling? So the cold plate two-phase cooling can dissipate high heat loads at much lower flow rates than the single-phase cooling, which means it can be more and more energy efficient. And the refrigerants have a high dielectric characteristic and evaporate at ambient conditions. And the two-phase cooling also allows absorbing the heat at a desired temperature by controlling the system pressure. So the dielectric fluids often have the saturation temperature as a function of the system pressure. So if you're able to regulate the system pressure, you can regulate the saturation temperature depending upon the temperature that is required by your device. So let's say that you want to regulate your device temperature to 60 degrees Celsius, then you can choose the fluid and regulate the system pressure so that the saturation temperature is closer to 60 degrees Celsius, so you can absorb most of the heat at 60 degrees Celsius. So for this, we wanted to first develop a bench level expander setup that can have a coolant distribution unit distributing the fluid through the loop and trying to remove the heat. So for the purpose of mimicking an electronic chip, we built a copper block that is capable of dissipating more than a kilowatt of heat, and on top of which we mounted this cold plate. And this cold plate is receiving fluid from this reservoir. So we have a pump system that can pump the fluid, and then we are able to monitor a lot of temperature and pressure within this cooling loop. So now we took a commercially available cold plate. The reason why we chose a commercially available cold plate is because it kind of includes a lot of this manufacturing constraints and it's more pragmatic. But we wanted to see if the commercially available cold plate design is an optimal design. So this is the commercially available cold plate's thermal resistance. We tested it. And then as we keep reducing the height of the films in the cold plate, we did see that the thermal resistance dropped, which really reconfirmed that there is a huge opportunity to optimize the geometry of this cold plate because the available geometry is not the optimal geometry. And now we just don't want to play with the height. We want to do a formal optimization on the height, the thickness of the fin, and the width of the channel, and all of that. So what we tried to do is we took this study forward, and then we tried to modify the design by varying the height of the fin, and then by creating more and more channels, the width of the channel, and all of that. And we wanted to do this in a formal way. So since there are very limited options to model the two-phase cooling, especially the liquid to vapor phase change, we did make use of a deep learning network which can be trained based upon the experimental data. So the cold plate geometry parameters were varied, and we did fabricate each of these geometrical parameter based cold plate, and we obtained the cold plate response parameters like the thermal resistance and the pressure drop. Since the thermal resistance and the pressure drop are oftentimes conflicting, we want to come up with a methodology that can minimize both of it. And we trained using the limited data that was available. So we had to do a lot of this hyperparameter optimization of this particular neural network because the data was really limited. It was always coming from the experiments. And we want to make sure that with the limited data, if you want to build a robust model, then we have to do a lot of optimization only within the model. So we did a lot of optimization, and then we found that 4 hidden layers with 8 hidden neurons each would give the best output for this very limited data. And we did use this neural network to drive a multi-objective optimization engine. And as you can see here that when we did this multi-objective optimization, we were able to get a very nice Pareto friend, which was trying to minimize both the thermal resistance and the pressure drop. And one beauty of the results that we saw here is that this design P3, which satisfies the thermal resistance and the pressure drop in an equal weightage, like 50-50, this design was not a part of our initial experiments at all. This was completely identified by the machine learning. So you can see that the machine learning can offer advantages like even identifying new designs that were not even thought about before, which can lead to very optimal design. So we developed guidelines on how a two-phase pump to two-phase cold plate designs have to be made by making a lot of inferences from this. Not only that, we also learned how not to design a cold plate for two-phase, because by making an inverse of this problem, instead of saying that I want to design a good cold plate, if I just pose it as if I want to design a bad cold plate, you can still get some designs that are very bad for both the thermal resistance and pressure drop, which can be an invaluable data on how not to design a cold plate. The next, what we wanted to do is the same cold plate. We want to test it on a data center in a more of a rack level approach. So for this, what we did is we chose a rack in our own data center, and we replaced the 17 air-cooled servers in a rack and retrofitted with two-phase evaporators. We had 2 CPUs per server and 1 server with very high power CPUs, and we replaced all of the air-cooled heat sinks with liquid-cooled cold plates. So a commercial coolant distributed unit is deployed here, and this problem is much more complex because on each server you have this cold plate. So the coolant distribution unit is actually sitting at the bottom, and it's trying to distribute the fluid to all of these servers. So you can see that these air-cooled heat sinks were replaced with this liquid cold plate. So this is a schematic of the experiment setup. So the cooling distribution unit transfers the absorbed heat in the server's loop to a chilled water loop via a liquid heat exchanger. And we had a series evaporator in 16 servers and 1 server with parallel modules. And we had 2 centrifugal pumps. And we did some instrumentation for noting the temperature, pressure, the flow rate, and CPU powers and temperature from IPMI data. So you can see that there are two cold plates in series, which means the fluid enters here, goes through one cold plate, gets heated up, and the heated fluid passes through the second cold plate. And you also see that the cold plates in parallel, where there is an individual inlet and outlet to two cold plates, so they are not thermally talking to each other. So the servers had, like the rack had a mix of servers, both having cold plates in series and cold plates in parallel. So the server 13, so this is a coolant distribution unit, and you can see that there are different servers from server 17 to server 1, and we did instrument all of these, but I'll be showing results for these 5 servers. So one thing is that as we move on the top of this rack, you can see that the hydrostatic pressure also changes. Since the hydrostatic pressure changes, the saturation temperature of the fluid received by each of the servers can change, which can really change the pattern in which each of these boil, because the server power and the server's workload, everything remains same. But because of the hydrostatic pressure difference, you can see that the coolant enters each of the server at a different inlet condition. So here, if I don't apply any heat, you can see that the flow rate of server 1 and 5 are affected significantly as the reservoir pressure decreases. So as the pressure decreases, you'll see the subcooling decreases, the rate of vapor generation increases, and because of which the resistance on the flow increases and the flow rate decreases, which means as the subcooling decreases, which means we are more closer towards the saturation condition. Because of the fluid entering the cold plate at the saturation condition, it picks up the heat readily, and then there is a lot of vapor generation. The generated vapor can cause a resistance on the flow because of the friction between the generated vapor in the liquid pool, because of which the flow rate will reduce, because the pumping power is kept constant. So the flow rate will reduce to tackle this increase in the resistance. And how do I detect a boiling in such a system is by using the pressure data and the flow rate data. As you can see here that as we load the servers, at the moment I see that the server flow rate rapidly decreases, it means there is a boiling happening because of the vapor generation. You can see that the server 1 and server 5 have encountered boiling, and then it is seen that their server flow rate decreases. And if you even look at the pressure at the edge, you can see that for the same servers, the pressure is also increasing, which is indicative of the boiling. So the heat load and its distribution across the rack can affect the flow distribution. So the system should be designed for the targeted heat load, the number of evaporators. There is a universal design will not necessarily either deliver nominal performance nor guarantee a reliable operation. So the next topic I really want to touch upon is the phase change material-based capacitance for portable electronics. So here the phase change, which is now we are talking about solid to liquid. So previously we did see about the liquid to vapor phase change and its research potential. Now we are talking about the solid to liquid phase change, which is more of a passive cooling technology. So there are a lot of opportunities in optimization of the transient thermal management system. So the objective one is maximizing the phase change time during the melting process without exceeding the device safe operating temperature. The second objective is minimizing the solidification time, because by minimizing the solidification time, you can make sure that the phase change material based heatsink is ready for the next duty cycle. So we want to do both of which simultaneously. So considering this, the constraints would be the maximum volume of the PCM that is available, and the thermal conductivity enhancers in the form of metallic films and porous media can be employed, and the geometry and the morphologies of the thermal conductivity enhancers are seen to have considerable effect on the thermal performance of the PCM composite. So when we have the heat flux, the solid to liquid phase change material based composite will melt, and we want to make sure that they solidify back on time. So the level 1 optimization is to determine the optimal PCM to the metal volume ratio, which will maximize the performance. And the level 2 optimization would be to, for a fixed volume ratio, determine the optimal geometry and the morphology of the thermal conductivity enhancer. And you can see that there's a conflict between the thermal conductivity and the energy density. So the more, if you try to increase the thermal conductivity more and more in a constrained volume, then you lose out on the amount of phase change material that you can have. So it's a combination of having metal and phase change material to really achieve the optimal performance. So just like selection of fluids for electronic cooling, we also have criteria for selection of phase change materials. So there are different types of phase change materials, ranging from organic phase change material to salt hydrates to metallic alloys. So for organics, the advantage is that they have a very high specific latent heat, high dielectric breakdown strength, and the disadvantage is like they have a very low thermal conductivity. So you always need a support of an external metal to improve the thermal conductivity. And applications would be transient cooling of silicon-based microprocessor. And for the salt hydrates, the advantage is that they have a very low cost and they are most corrosive and suffer from phase separation. And the applications would be building energy conservation, power electronics, and high transient applications. For metallic alloys, the advantage is they have high volumetric latent heat, high thermal conductivity, and they are most expensive. So the performance metric for phase change materials, if you look into the literature, they are mostly categorized into three performance metrics. The first performance metric is called the cooling capacity figure of merit, which is a square root of the product of thermal conductivity and latent heat. So this can be easily calculated from material properties, but since they are just based upon the material properties, for different operating conditions, you may not be able to be quite certain that this phase change material will maximize the performance. So it does not include the effects of operating conditions and geometry. And the time to reach set point temperature is another figure of merit that is oftentimes used. The time to reach set point temperature during the melting process, and the time to reach set point temperature during the melting and the solidification process. So this time to reach set point temperature during the melting and solidification is very important because it characterizes the entire operation of the phase change material based heat sinks. But the problem is they are computationally expensive. So here you can see that if I just use the figure of merit based upon the material properties, I can see that if I want to minimize the temperature and if I want to also prolong the time of operation, the optimal PCM volume fraction from this dotted curve seems to be close to 50%. But the moment I start doing my simulation and they start varying my operating condition, you can see that the optimal is no more 50%. It can actually vary. So it is confirmed that the operating conditions and the geometry can have a significant impact on the optimal configuration of your PCM based technology. And we also have published a paper where we demonstrated that as the heat flux amplitude increases and if your surge duration is really reduced, which means it's highly transient, you can see that sometimes using a phase change material can be harmful because the heat is not able to actually access the phase change material due to its low thermal conductivity. So there might be certain operating conditions where it's better to use just pure metal copper rather than to use phase change materials. And it is important for us to identify such regions as well because they can really be a precursor and help us select if we really want to use phase change material for a certain application or not. So for this, what we did is we took a real smartphone and we wanted to do like a lot of applications like video calling and Instagram chatting and all of that, and then try to see if they would cause if the phase change material would be of any advantage in such applications in real time. So we took a smartphone and then we switched on the applications and we embedded the phase change material based heat sinks on the backside of it. And you can see that while we are operating the smartphone, there is a significant advantage in terms of temperature we can get. And the smartphone was kept really below its safe operating limit for most of the time. So you can see that if I don't use a PCM, the temperature is much higher compared to what happens if I use a PCM. So you can see that there's a huge temperature gain that we are getting. So PCM is certainly advantages in the intermittent operation, and we can continue to do a lot of research on optimizing the phase change material based composite. So finally, I want to touch base upon the cooling limits for two-phase immersion and embedded cooling. So today the two-phase immersion and embedded cooling is gaining a lot of traction because the heat flux of the electronics is continuously increasing, and we want to make sure that we are able to develop cooling technologies that can really address these thermal challenges. And as you can see here on the y-axis, you have this heat transfer coefficient, and on the x-axis you have this critical heat flux. And of course, we can see the literatures that have been using liquid water seems to give them a very high critical heat flux. And you can also tailor the enhanced surfaces like films in such a way that you're also able to reach a very high heat transfer coefficient. But the one on the bottom left, the points that are grouped here, which correspond to very low critical heat flux and low heat transfer coefficient, are mainly due to the use of dielectric fluids. So you can see that as the chip hotspot size is less than 1 centimeter square here, that's where most of these points are. And you can also see some of the points corresponding to the hotspot size of 1 centimeter square and greater than 1 centimeter square. So this says that liquid water has a huge potential even on phase change cooling. But the problem is that you have to stop the interaction between the active electronic circuits and the liquid water. And the next emerging area is the silicon embedded cooling limits. And you can see that when we are trying to embed the cooling technologies directly onto the silicon, we can reach more than 1,000 watts per centimeter square. So the literature from Drummond et al. In collaboration with IBM, they demonstrated that they are able to remove 1 kilowatt per centimeter square of heat compared to what Tuckerman and Pease have done in the past. So the Tuckerman and Pease have done like 790 watts per centimeter square, but today we are able to see literatures that are talking about more than a kilowatt per centimeter square. So we want to push the paradigm and then cool more and more. So we have to really look for more of the phase change material based cooling. So if you're interested in other groundbreaking works, there is also an illustration of UCLA developed solid state thermal transistor using an electric field to control the heat movement even before the cooling channels are able to pick up the heat. And we also see the passive saltwater cooling boost CPU performance of almost 33%. So there are some innovative cooling technologies, innovative cooling fluids that are being researched, and people are trying to publish a lot of results on that. And there is also a huge interest on India Semiconductor Mission, where the government is promoting a lot of research on semiconductor manufacturing and semiconductor research. And thermal management of electronics has been identified as one of the 12 strategic research areas with respect to India Semiconductor Mission. So as a summary, the initiatives are at the forefront of research and development, pushing the boundaries of what's possible in terms of cooling technology. And by focusing on innovative approaches such as microfluidic cooling, advanced materials, and smart thermal management techniques are revolutionizing the way we manage the heat in electronic devices. And as we continue to ask more from our devices, whether it is in the realm of high performance computing or artificial intelligence or data centers, we must remember that efficient thermal design will be the enabling factor for the next generation of high performance computing. And heterogeneous integration will drive the technology for the foreseeable future. And heterogeneous integration will bring about new challenges with respect to the thermal because of the packaging constraints. And machine learning driven multi-objective optimization will enable global optimal solution for the future electronic packages. And there's also the famous quote from Swinnen from ANSYS: we can design and manufacture incredible chips, except they will melt. It is no more a manufacturing limitation, not a design limitation. It is a thermal limitation that we can't get more heat out. So I thank you all for your attention, and I'll be open to questions and any feedback, or if you want to ask any doubts. Thank you.
Dear participants, I request you all, if you want to interact with the expert. Professor, I think there's no question. We are grateful and delighted to have you an expert for today's lecture. So I think everyone had a great learning experience from your research and your experience on the electronic cooling.
Thank you, Dr. Satyendra.
Yeah, I hope there's somebody unmuted. Still, participants, if they want to interact, they can interact with the professor. Okay. Thank you very much, Professor.
Thank you very much, Dr. Satyendra, and thank you so much to the audience. So if anyone has any doubts post this talk, you can feel free email me, and then I'll be happy to respond and answer if you have any questions. Thank you so much.
Thank you so much for your valuable time, sir.
Thank you.
So, dear participants, we'll resume the short-term course tomorrow from 10 a.m. to 12 a.m. for the morning lecture, and then in the afternoon from 3 p.m. to 5 p.m. we will having a lab session. We're having expert from the Godrej who will be taking the lab in the evening session. So for the morning session, we have the expert, uh, Professor Arvind Kaprit from Oslo University. So he will be delivering his lecture on AI and ML uh, optimization on wind turbines and some other related thermal systems. So I hope you will be having great learning experience tomorrow as well. Thank you very much for joining for the first opening day of the short-term course. And for your information, let me tell you, the same link will be used for all the 5 days, for all the remaining 4 days now.
Sir, hello.
Hello.
Hello, sir. Can you provide recording, sir?
Yes, of course. Let me share with you the link of the YouTube streaming where you can access the content anytime.
Okay. ठीक है.
Link I have shared in
Thank you,
the
sir.
WhatsApp group actually. Am I
Yes,
audible?
yes, you are clearly audible, and I also shared in the message.
Link actually we have shared. You can stream the live video or you can see whenever you want, okay, from the YouTube.
Okay, sir. ठीक है. Thank you, sir.
Okay, thank you. Is there any further inquiry related to short-term course?
डॉक्टर सुंदर इसकी इनकी वो मिल सकती है स्लाइड्स वगैरह इनका रिक्वेस्ट कर सकते हो?
Yes, sir. I will send an email to the professor.
हाँ, क्योंकि इनका काफी फास्ट था, बहुत ज्यादा.
जी.
ये फास्ट काफी काफी पेस में प्रेजेंटेशंस रहे. So we will ask sir to from the answer. If he will be agree, then we will share. Okay, if there is no further query, then we will resume the sessions tomorrow from 10 a.m. Thank you all.
Thank you, sir.